Next, we'd like to change equations written in logarithmic form to exponential, and conversely change equations from exponential form to logarithmic form. This is a very important skill that we'll be using in the next couple of sections, so you'll need to be able to go forwards and backwards from these two forms rather quickly. I rewrote the definition of the logarithmic function in both forms. I want you to know that log base b of x equals y is the same thing as y equals log base b of x. It doesn't really matter if the y is in the back or the y is in the front. It doesn't really matter to me. You can do it either way, but some students prefer just to do it one way every single time, so that way they don't have to think too much about where it belongs, and that's fine by me too. But if you see it written the other way, I need you to understand that it's the same thing, whether or not your y equals is in the front or your y equals is in the back. So these equations are already written in log form, and I want you to change them to exponential form. I don't want you solving, I don't want you to do anything else but changing from one form to the other. We'll get to solving in a little bit, but for now we're just trying to change from one form to the other. First thing I like to do is look for the base, because the base is the same in both logarithmic form and exponential, although the base is written as a normal size base in exponential. 5 to the some value equals some other value. But remember that the 2 and the x switch sides. So the 5 is not going to be next to the x now. The 5 is going to be next to the 2. The 2 is now going to be the exponent equals x, and that's the argument. So rewritten in exponential form, we have 5 to the 2 equals x. You may want to pause the video right now and see if you can do the next two on your own. Looking at the next problem, we have 3 equals log base 4 of 64, and I need you to understand that that would be the same thing as saying log base 4 of 64 equals 3. And if it helps you to rewrite it the same way every single time, I don't really care if the equation has a log in the front or if this is a log in the back. It's really the same thing. These are both written in logarithmic form, and I want to change it to exponential form. So I'm going to look for the base. And the base on either one you want to look at is 4. Notice it's a normal size 4. 4 is raised to the 3, or third power, equals the argument, in this case 64. And our last problem says ln 7 equals y. This is in logarithmic form, and you want to change it to exponential form. But we don't have a base here. There's no base at all. Does that mean there isn't a base? Well, no, there is a base. It's just an invisible base, and because it says ln, we know that the invisible base is base e. Now that we know we have a base e, I can use that in my exponential form. E raised to the, we only got two choices, 7 or y, and because we're changing it to exponential, the 7 and the y switch sides. So the e is now going to be with the y, and the 7 is from the argument is now going to be by itself on the other side of the equation. So these are the exponential forms of the logarithmic equations. Next, we're going to do the same thing backwards. Here I have an exponential form of an equation, and I would like to change it to logarithmic form. So the first thing I like to do here is start with an log. Because I need it to be in logarithmic form, I start with an log. Then I need a base for my log. And the base for my log is going to be 12. 12 is the base of the exponential, so 12 is the base of the logarithmic. Don't forget that the 2 and the x switch sides, because the 12 was with the 2 and the exponential, the 12 is going to be with the x. Notice log and x are normal size, 12 is little and low. Equals, the only last number we have is 2. You may want to stop the video right now and see if you can do the next two on your own. The next one I have log base, and the base that I have is b. We need an argument and the exponent here are going to switch sides, so I have log base b of 8 equals 3. And the last one, e to the y equals 9. I have log, L-O-G, base e. Base e of the 9 and the y switch sides, So base e of 9 equals y. Now normally I would be done here, except because we have a special base, the special base e says that I can reduce this even further. Instead of writing log base e, well, no one really writes log base e, we write it a little bit more simplified. Because e is such a highly reoccurring base, we have a simplified form. Instead of log base e, we write ln 9 equals y. We don't write the base at all. ln is an implied base e. So please, please, please do not write log base e of 9 equals y for your final answer. It's okay to be an intermediate step, but the final answer needs to be ln 9 equals y. The next topic we're going to be looking at is evaluating logs without a calculator. I want you to be able to look at some simple logs and be able to figure them out without a calculator. We will be talking about how to type them in a calculator in a little bit, but for now I want you to be able to evaluate logs without one. When this is possible on your homework, it will say evaluate without a calculator, or on your exam. If you need a calculator, then it won't ask you to do it without a calculator. So not every log expression can be evaluated without a calculator, but some can, and we're going to show you how to do those. Step 1 is I want you to set the log equal to x. Log expressions are hard to evaluate on their own, so we are going to make it a log equation. An expression doesn't have an equal sign, so I'm adding an equal sign to be able to manipulate the equation, solve for x, and then I'll be able to answer the expression. Step 2 says switch the log equation to exponential form. Once you switch it to exponential form, it will be easy to solve for x. Once you've solved for x, I want you to then remove the x from your answer. We are the ones that set the log equal to x. We are the one that brought x into this problem. So at the end, we have to take it out of the problem. It wouldn't make sense to answer an expression written x equals. We are the ones that put x in. We're going to take it out at the end. So on the first problem, we have log base 2 of 16. I set it equal to x. That was my choice. And the reason I chose that is because now I can change it to exponential form. An exponential form says 2, my base 2, to the x equals 16. And hopefully these problems will be simple enough that you'll be able to do them in your head. 2 to the what equals 16? Well, I know what that is. 2 to the 4 is equal to 16. Because 2 times 2 times 2 times 2 equals 16. So 2 to the 4th is 16. And that's just a fact that I happen to already know. Now I'm going to remove x from my answer. So my answer should be log base 2 of 16 is equal to 4. You shouldn't have any x's in the problem because I'm the one that brought the x's into the problem. I have to take it out. On the next problem, we have log base 3 of 9 equals x. I let it equal x so that I can change it into exponential form, which says 3 to the x equals 9. Can you figure out what 3 to the what number equals 9? Well, 3 squared. So that means log base 3 of 9 equals 2. Looking at the next problem, log base 25 of 5, I don't know what that is, so I'm going to let it equal x. I let it equal x, so it's an equation. So now that I can change this equation into an exponential equation. 25 raised to the x power equals 5. Notice the 5 and the x are switching sides. So now I'm trying to figure out 25 to the what equals 5. This one's a little bit harder than the last two. I know that the square root of 25 is 5, but that's not an exponent. Well, the square root can actually be rewritten as an exponent. And the way we write that is 25 raised to the 1/2. 1/2 is the same thing as the square root, which still gets me to 5. So 25 raised to the what? Well, that's a half. So we have log base 25 of 5 equals 1/2. In a few sections from now, we'll be solving some more of these log equations, which are going to be a little bit more difficult. But for now, all the ones that you'll be given, you should be able to figure out in your head what is the value. When you raise the base to it, you get your argument. After some practice, some students may not want to write all these steps out. They'll just look at the base and the argument and say 2 to the what equals 16 in their head. 2 to the what equals 16. Well, okay, that's 4. So 2 to the 4 equals 16. Or just looking at your base and your argument, 3 to the what equals 9. Oh, yeah, 3 squared. Or 25 to the what equals 5. Oh, yes, a half, because a half is the same thing as a square root. So if you don't want to write out all these steps, you may not have to once you get good at evaluating these logs without a calculator. I have 3 more examples for you. Log base 7 of 7, that's a little interesting. Notice that your base here is the same thing as the argument. So I let log base 7 of 7 equal x. So that gets me 7 raised to the x power equals 7. 7 to the what gets me 7? Well, I know that 7 to the 1 is 7, so that means my x is equal to 1. Therefore, log base 7 of 7 equals 1. Well, that's interesting. When I have my base and my argument the same, it looks like I'm getting a 1, because you're thinking in your head, 7 to the what is 7? Well, 1. So this actually can be generalized to a rule, and the rule is log base b of b will always be equal to 1. As long as your base and your argument are the same, log base b of b is going to be equal to 1. Now, this next problem is almost exactly the same, except we have log base 7 of 7 squared. So in this case, we actually have an exponent on the argument. That's interesting. Let's see what happens here. Let's let this equal x and change it to the other form. 7 to the x equals 7 squared. 7 to the what equals 7 squared? Now I know I could square out 7, and 7 squared is 49. I could do this, but I think it's even more simple than that. 7 to the what equals 7 to the 2? Well, if my bases are the same here, then my exponents must surely be the same, so x has to then be 2. 7 squared equals 7 squared? Absolutely, that is correct. So that means log base 7 of 7 squared equals 2. Just like in our last example where the 7 base and the 7 argument, it really didn't matter that these were 7s. It just mattered that they were basically the same value, that the base and the argument were the same value. Same thing's happening here. As long as this base, 7, and the base of the argument, 7, are the same, my answer is going to be the exponent. This problem can be generalized to a rule, and the rule says log base b of b to an exponent, we'll say r. The log base b and the exponent base b essentially cancel each other out, and I'm just left with my exponent r. Our last example here, I'm going to set my log equal to 0 so that I can change it into an exponential form. 5 to the what? X equals 1. 5 to the x equals 1. What value of x can I plug in here to make this statement true? Well, I know that any number raised to the 0 power is 1. So as long as x is 0, I know 5 to the 0 is 1. Therefore, log base 5 of 1 equals 0. Notice how I said as long as the exponent is 0, the base can be anything it wants to. This 5 kind of doesn't really matter. If you have an argument of 1, the only way you could raise any base to an exponent to get a value of 1 is if you raise it to 0. So this can be generalized to a rule as well. And the rule here is log base, well, anything, b, of 1 is going to be equal to 0. These three rules we're going to rewrite on the next page with several other rules called the properties of logs. Log base a of a is always going to be equal to 1. You're thinking in your head, this base a raised to the what power equals a? Well, 1. On the next problem, log base a of 1, well, a raised to the what is going to equal 1? Well, that's 0. A raised to the 0 is always 1. This third one we did as well, log base a of a to the r, a to the what equals a to the r. A to the what equals a to the r. Well, as long as my bases are the same, my arguments have to be the same, so in that case, r. Another way of thinking about this is log base a and the base of the exponential. We know that the bases are the same and that log and exponential are inverses of each other. So another way of thinking about it is this log base a and this base a are essentially undoing each other. They're undoing each other because they are inverses. And what are you left with? R. But remember that the r is a normal-sized r. Similarly, we have a raised to the log base a of r. Another way of thinking about this is base a of the exponential and log base a. Notice that the bases are the same. I'm taking an exponent of a log, and logs and exponents are opposites of each other, so they kind of cancel each other out, and I'm still just left with a normal-sized r. On the right-hand column, we have a few more properties, but these are basically the same properties as the ones on the left, except with ln base, we're talking e all the way down here. You can think of there's a base e on all of these ln logarithms. So ln base e of e, although no one really writes the base e, I just go ahead and write it in there for you so you remember that the ln does have a base, it's just base e. Well, when the base e and the base of the argument are the same, my answer is always 1. Because e to the what equals e? Well, e to the 1. How about the next one? E to the what equals 1? 0. On the third problem, e to the what equals e to the r? Well, if my bases are the same, the exponents have to be the same, and that's just r. Notice these are the exact same properties. Instead of any base a, it's the base number e. And on the last problem, we have my e and ln also canceling out, and I'm just left again with r, for the same reasons on the left column as the right column. If you'd like to memorize these properties, you're welcome to get your answers a little bit faster. Let's do the next 4 problems a little bit faster here. Log base 15 of 15 is equal to 1. Whenever the base and the argument are equal to each other, your answer is 1. Log base 9 of 1. Well, whenever your argument is 1, your answer is 0, no matter what the base is. Log base 7 of 7 to the 8. The log base 7 and the base 7 of your exponential essentially cancel each other out, or are inverses of each other, and you're just left with 8. Similarly, 3 raised to the log base 3 of 17. The base 3 of your exponential and the base 3 of your logarithm are opposites of each other. They inverses and they cancel each other out, leaving you just with 17. Hopefully these would be some quick problems on your homework and your exam that you'll be able to get some easy points on because they're just straight properties.